Okay, welcome to the last part of our sessions here on A-level quantum mechanics. Today we're going to look at wave-particle duality. And this is the kind of final piece of the puzzle where we're going to put it all together. And this is where you really earn your A-star, because there are a lot of nasty questions here that CIE put. And this is not something that you can get by just kind of guesswork or just memorizing mark schemes. You really have to understand this. Now, the individual pieces are quite simple, but putting together they are tricky. So we need to look at how different things give us evidence of particle nature, of both electromagnetic radiation and wave nature. And then we need to do the same thing for electrons as well. Once we've got that, we're then going to look at the de Broglie wavelength, which is associated with a moving particle, and we're going to use the equation that he gave it. So these ones are actually, they're mathsy, these are the easy bits. It's this bit here that is where you kind of earn your marks. Alright, so light behaves quite strange, and we went through the whole first lesson where we talked about how we have lots of evidence from the behaviour of light that light is definitely a particle. If you remember, we can say that for the photoelectric effect, it occurs only ever above a threshold frequency. It doesn't matter how intense you make that light, it will never occur below that threshold. Now, all the maths, all the explanation of how a wave works doesn't work like that. It shouldn't be possible for that to happen, because we know that if you think back to year 12, that the intensity of a wave, which is a measure of how much energy it imparts, that's proportional to its amplitude. So we should be able to give enough energy from a wave just by having it with enough amplitude and enough intensity. We can't. That's evidence that it must be a particle. Similarly, it happens instantaneously. Even if you have a really dim light source, we still see the photoelectric effect instantly. And again, that shouldn't happen. We should see it taking a significant amount of time. Or if it's very low intensity, it should take time to build up. So, and there's other things as well, like the fact it's instantaneous. Sorry, I just said instantaneous. Yeah. However, you spent all of year 12 learning about how double-slit diffraction works and about refraction. And those things can only be explained by light being a wave. There is no possible particle model that explains diffraction. So light has to be both a wave and a particle. And oh dear, it turns out, so do electrons. So we've talked for years about electrons being a particle, and you can watch them. You can watch them being an individual particle. If you have pair production in a cloud chamber, or particle accelerator, you can watch an electron pop into existence and you can see it moving. This is the path that an individual electron took. This is a photograph of it. We've shown this electron being a particle. But it also turns out that if you get a beam of electrons and you shine them through a double slit, well then what you get is an interference pattern. And in the lesson we're going to show that. What we get is a thin graphite screen. Now, graphite, it acts a bit like a grid, so we have horizontal and vertical slits, and they're all kind of arranged in different ways, and we can kind of show this with diffraction gratings. When you have that particular arrangement, you actually get a circular diffraction pattern. The maths is a little bit nasty, so we won't go into the maths of it, but you can just do it with a pair of slits, and I'll show you that it works with light, and you see the exact same thing with electrons. So we have this same problem. Electrons, they're particles. We know they're particles, but they also must be waves, and neither model explains the behaviours of the other. It has to be both, which is why we call it duality. So it was a lot of work was by this chap. His name is de Broglie, not de Broglie, de Broglie, and he said, well, let's imagine that electrons travel as a wave, and when we get to this really advanced level of physics, a lot of what we do is guesswork. So they came up with an equation and then he used experimentation to prove that his equation was correct. So he proposed that the wave-like particle, or the wave-like nature of it, could be represented by its wavelength. And the equation that he came up with is that the wavelength is equal to Planck's constant divided by momentum. Remember, we use P for momentum. Now, unlike light, electrons do have mass, so we can then also say it's mv. And what we discovered is that actually this applies to all matter. It doesn't matter, It doesn't matter what the matter is. All matter actually has its own wavelength. So why don't we diffract as people? Well, if you think about what Planck's constant is, Planck's constant is already tiny, and we're dividing it by something, so when you divide by something, you get even smaller. So Planck's constant, we start with something absolutely minuscule, and if you think about, say, the momentum of a person, even when you're sitting still, you've got a small amount of motion to you, and your very large number for your mass is going to be nowhere near big enough to turn lambda into something that is sort of smaller than a trillionth of a nanometer. And we'll do that. One of my favourite questions is we're going to work out how slowly does a camel have to go to diffract through the eye of a needle. We'll watch out for that one. It's going to be fun. So we don't notice it day to day because this is tiny. Usually momentum is big. So tiny divided by big means that we get a tiny wavelength. So those wave properties, we just don't observe them. We don't see it diffracting. And if you remember again from year 12, let's say you have a gap like this. We know that we get the most diffraction when the wavelength is about the same as the gap. So you would need unimaginably small gaps in order for most things in classical physics to ever observe this wavelength, this wave-like properties. But when we get onto electrons, and we're talking about these electrons, well, electrons are quite light. We can make them travel quite slowly, and we can make these gaps very, very small. So we start to be able to observe it. And that's really it. When we think about kind of what we actually need to know, you need to be able to describe the evidence, you need to be able to use this wavelength, but that's kind of all that CIE ask of you. So I just thought, just to make sure you have enough time on this video, I just show you one more experiment because it blows my mind still. And I've done this one. I've actually done this in a lab during my undergraduate degree, and it's quite a cool experiment. What you get is a light source at one end, which is a light bulb, and it's just a very old school incandescent light bulb, so one that's adjusted with a light source and you can turn up or down the power of it to make it brighter or dimmer. And at the other end you have a detector box. And in the detector box you have a single, it's called a photomultiplier tube. And that is an incredibly sensitive light detector which can literally detect single photons. So you get a little pulse of electricity out of these every time they detect individual photons of light. Now what you do is at this end you put a double slit, and then you adjust your DC power until your photomultiplier tube is going pip, 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 pip to show individual electrons appearing down it. And then what you do is you move this detector backwards and forwards like that in order to detect light that arrives at different places. And what happens is over here you see first one single dot of light arrive. Boop, there it is. And it has some friends as individual photons of light appear. And as time goes by, you see this, which is clearly a diffraction pattern. And that just doesn't make any sense at all. Because what that means is an individual photon is being produced at this at the lamp by, like we talked about last lesson, it's being promoted up into a high energy level, it's dropping down into an electron is being promoted to a high energy level, the electron's dropping down, that's emitting a single photon of light. And that photon of light is travelling down this box. And somehow as it does that, it passes through both slits simultaneously and interferes with itself, acting as a wave, and then it arrives at this photomultiplier tube, ping, and gives us a single dot of light, where it must be acting as a particle. And that, I think, really sums up wave-particle duality. It's not that they sometimes act like one way and sometimes act like the other. They are acting both ways all the time. And we still don't really understand how or why. But it gets even weirder. You can do this exact same experiment with electrons. And if you do it with electrons, you obviously have to pump all the air out, and you use a beta source at one end, and you can send individual electrons firing down here, and you get the exact same damn thing, but you can make it even weirder. And this isn't on your course, but I think it's pretty cool. What you can do for electrons is you can put a loop of wire around just one of your slits. Now, when the electron moves through that loop of wire, you've got a charged particle going through a coil. So that will actually induce a very, very tiny voltage. So you can use that to tell which of the two slits the electron went through. And do you know, if you do that, if you find out which one it went through, you don't get this pattern anymore. Instead, you just see one band and another band, one behind each of these slits, because it suddenly acts like a particle the entire way around. So somehow, by observing this electron, by forcing it or by knowing which one it goes through, you actually make it act like a particle the whole way. And if you've ever heard of the term Schrödinger's cat, this is where Erwin Schrödinger said, well, that's nonsense and insanity, and he came up with Schrödinger's cat as an idea of this is all madness. But it's not madness. We can do it. It's experiments that can be done. We can absolutely prove that they are correct. And I think that's probably where I'm going to leave you today. It's just be aware, as A-level students, you're nearly at the end of your course. Physics is really cool. There is still a huge amount of stuff that is exciting about there. Now, what I hope you've learned from your A-level is it's all explained by maths. Physics is just maths in disguise. But the stuff that we're learning is still really cool. It is the fundamental workings of the universe. And yeah, you can go and do a degree, and if you do a degree in this, you'll understand an awful lot more. A lot of this will make a lot more sense. You need crazy hard maths to do it, but it can be done. But don't lose the sense of wonder about it, because it is explainable, it is logical, but it's also weird and cool. And that's why quantum mechanics gets misused by a lot of people. It's why it gets used to support things like homeopathy or quantum water and all sorts of things that are scientifically nonsense. But that's because it's non-intuitive, and that's because it's weird and cool. Anyway, I've now made you listen to my little philosophy of physics rather than just your A-level, but I hope you feel it was worth it. Remember, this bit, that's the easy bit, right? The equations are simple. What you need to do is be able to list all of this evidence, and for each one say which version of reality it fits with, and talk a little bit more about those experiments, because it's that kind of hand-wavy talky stuff that is where, like I said before, you earn your A star.